Here's the 1379 to 1 gearbox with a shaft mounted on it that looks lovely. And I am going to push on this with it mounted to my 3D printer box and see if the input shaft will spin 1000. Actually, it would only be like, oh, we've got 30 degrees here, so 30% of 1379. And let's give it a try. Today on Geared On For What, we're going to be testing gear ratios of differential planetaries. How much of a torque advantage do they have, and how much torque can they handle before the gear teeth start to strip off? Let's go. So I got a lot of comments on my differential planetary videos. These are the videos with the huge gear ratios, because basically what I've done in those videos is taken 3 of this gearbox, that is 3 of these, and stacked them. So in those videos with the really high gear reduction, basically what I've done is I've taken 3 of these differential planetaries without this handle on them, and I have put them in series. And I went through all this stuff and how you get the gear ratio when you do that and everything, but I got a lot of comments asking me to back drive this gearbox, to basically grab this handle and crank it so I can get the input of this gearbox to spin 1379 times for 1 rotation of this output. And a lot of people really want me to make a video of that, so that's part of what I'm going to try today. But I'm gonna also mount this up here, like I said, and hook it up to this pail like this one is now, and see how much weight I can lift with this gearbox just the way it is, with just the addition of this arm. Now this arm is 6 inches center of this circle to center of this gearbox, and what that does for me is it makes it so I can easily calculate by how much this pail weighs, how many foot-pounds this gearbox can output before it starts to lose some gear teeth. And that's assuming that I will hit that limit. I may or may not. We'll just have to find out. So since I have the base for this test arm mounted up here, I'm going to first start off talking about this gearbox. And this gearbox is actually almost the same as this gearbox. Now, in terms of a differential planetary, these are the same thing. The difference is this one has a much higher gear ratio, and this one has a 3rd module. Now, a 3rd module seems to be the most important thing I've found with differential planetaries when it comes to actually being able to use the torque advantage that they give you. And that is because when you run, if you look at one of my older videos, you've seen that I ran this with a drill and held the output, and I ran it until these planets actually went in there and they went crooked inside the gearbox. Now when you add a 3rd module to a differential planetary, what you're doing is adding that much extra support for the planet gears against a side-to-side play from the sun gear when it's spinning. What I've done with this mount up here, I know this is far away for you, is I've actually supported these 2 outside rings together, so they're at the same potential in this mount. And then this center ring is attached to this demo arm. So this gearbox is only 43.3 to 1 for a gear ratio, and that is compared to this 1379 to 1 for a gear ratio. Today we're going to find out which one can handle more torque and how important adding a 3rd module is to a differential planetary. So I'm going to go ahead and put this one back in my mount, which is just putting the demo arm on. Okay, there we go. I got it back. So first off, I'm going to just demonstrate this thing moving up and down. And what I've got here is I took apart, I needed a way to drive my gearbox that I built for a stepper motor for a NEMA 17, and I didn't want to have to specially make a shaft for it, because who wants to do that? So what I did was I took the shaft out of a crappy stepper motor that I own, and then I took the back bearing off of it, and I'm going to put that into a drill. Now the reason I decided not to do this with a stepper motor is because the point of today's video is going to be about how much torque can a 3D printed gearbox handle, not how much torque a NEMA 17 motor can deliver to it. Otherwise, if I was going to do about the NEMA 17, it wouldn't really make much sense with 3D printing stuff, would it? Okay, so just to demonstrate, wrong way. This gearbox actually works reverse. So lifting the empty pail, setting the empty pail down. So for now, I'm just going to try some empty, or some not empty water bottles. And I'm doing this because if the pail falls, I don't want water everywhere. So then I'm going to lift this pail up off this scale. Let the scale go to 0. Set the pail back down. Release the weight from this arm. So I've got 3 pounds, 13.7 ounces. And without the water, the pail weighs 6.2 ounces is the weight of the pail. Can you see that? Hell no. 3 water bottles. 3D printed gearbox, lifting them up at 6 inches away from center, and let's give it a go. So I just attached the motor onto the stepper motor shaft that I mounted in there. Put the drill in reverse because it's backwards. And so it seemed to have no trouble with that. Alright, since this gearbox didn't seem to have any trouble whatsoever lifting up 3 water bottles, I figured I'd get one more. 1, 2, 3, 4. I guess that's all that fits in the pail. If it can lift these, I guess I'm just going to have to fill it up with water. So turn the scale on. And this weighs 5 pounds even. Alright. So I'm going to hook my drill up to stepper motor shaft again. Oh, before I forget, this thing is downloadable on Thingiverse for free, if you guys are interested. Okay, 5 pounds at 6 inches from center. Well, I think I heard some bad noises there, kind of jerking it around like that. It didn't like that at all. I took the planetary gears out of alignment, and now they're rubbing on each other. So now I pretty much have to take it apart and fix the gears. I think I could have avoided that if I would have built a more sturdy stand for this. Had I known when I built it that I would be using it to lift up 5 pounds at 6 inches away, which is 2.5 foot-pounds. Is that correct? My math, 6 inches away. So if I was 12 inches away, it would be equal to half as much weight. So 2.5 foot-pounds. How's that sound? I'll put a conversion on the screen. I guess I didn't have to tell you that, did I? Anyways, I'm done with this gearbox. Now I'm going to take it apart, show you guys what's inside it. I guess I could let you see what I'm doing, huh? That'd be nice of me. So, just to show you guys what's inside this planetary gearbox, it's got 3 ring gears. Here's number 1. Here is ring gear number 2. First, let's see if I can figure out what went wrong with it. Not sure anything went wrong with it. Why was it so hard to turn? So this is, I just took off ring gear number 2 and ring gear number 3, and it's got 4 planets. So except for the 3 ring gears, here's everything that's inside this gearbox. 3 sun gears and 4 planet gears. So in the newer designs of this, I've gotten this down to just 1 sun gear, which is basically just the 2 outside sun gears combined together to create 1. And the reason I've done that is to support the planets better. So this sun gear goes here, and this sun gear goes here, and the longer gear here is the planet gear. Now when I do that, when I connect the two sun gears on the outside together and omit the one in the center, what it does is it supports this planet against this side-to-side play that it seems to have a lot of trouble with. And it has the most trouble with that, and back to this 1379 to 1. Because when you look at this, you see, where's the torque coming out? The torque is coming out of this back ring, and it's being supported by this front ring. So if I turn this back ring, the planet gears are going to want to twist this way when I crank this back ring. So one way I could really improve this design is to add another front ring back here and extend the planet gears, and then turn the sun gear into, well, get rid of this sun gear, just omit it, and then put another sun gear just like this one back here. Now, just to give away a little secret for how this thing is working, okay, you see how it's a little bit bigger in the middle? That's what the gear ratio is coming from here. So the middle gear actually has the same amount of teeth as the two outside planet gears, and of course I call them separate gears, but they're actually combined together, so they are one. And then the ring gears have different numbers of teeth. And then ring gear number 1 and number 3 are exactly the same, with just a different number on them. I hope that helps some of you understand what's going on here a little bit better. And this is one of the reasons that I created this gearbox, because I knew that this wasn't going to work very well for torque, but I did know that it'd be really easy for people to understand. Alright, it is time to take that mount down, mount this one up there, and see how much weight the 1379 to 1 gearbox can handle. Let's give it a shot. Talk about a dull drill bit. Can't even drill a hole in plastic. Yep. And now, the answer to the question that is clearly on everyone's mind. How much torque can a 3D printed gearbox handle? Let's find out. So I'm feeling pretty confident with this one. So I'm going to start out with 5 pounds, 1.5 ounces of weight, and hope that it can do that. I suppose I should take this full one off though, shouldn't I? Okay, unfortunately I can't show you without dismounting my camera and messing up my whole setup. But it is 4 pounds. You can just weigh water bottles. How's that? Still 4 water bottles. This last one. And come on, buddy. And let's give it a go. There it is. Back up a little bit so you can see the whole operation. You know, this whole apparatus looks strangely like something they taught us about in high school. Ugh. Didn't plan that. We need more weight. What am I gonna do? You know what? I'm just gonna get some water. Okay, 0, and we are at 7 pounds 8 ounces. It's really not that much more than we had before, except it's a lot more risk now. So that makes things fun, right? Okay, I might kind of get my hand in here because I really don't want to lose this much water. There you go. 3D printed gearbox supporting 7 pounds of water. Surprised? Oh god. Okay, so as you guys could see there, it did work, but not for long. The gearbox was skipping teeth as it was going down. It could not handle that much weight. So what I'm going to do now is I'm going to attempt to back drive this gearbox. Yeah. Alright, you guys ready? Get real close with this. Here's the 1379 to 1 gearbox with a shaft mounted on it that looks lovely. And I am going to push on this with it mounted to my 3D printer box and see if the input shaft will spin 1000. Actually, it would only be like, oh, we've got 30 degrees here, so 30% of 1379. And let's give it a try. That didn't work out very well. The results aren't so good. I guess I didn't build this to be very structurally strong, and so the ring just snapped. Let's see what kind of infill I used here. Looks pretty solid. Maybe 50-60%. So yeah, back driving the 1379 to 1 is a no-go. It don't work. Anyways, I'd like to thank you all for watching. I wrecked my gearbox, but don't worry, I have a lot more of them. And we'll be making more videos. I would like to make more videos on the modular tore apart robotic arm, and I will. And I'd also like to make videos on taking the differential planetaries out of here, which are not the same as this one that I showed you. That's all over now. They're not the same. They have 4 modules, so they're even better, right? Oh, grease everywhere. Anyways, thanks for watching, guys. If you like this video, I have many more of them. Subscribe to the channel. Leave a comment. I love those. And put a like. Thanks.